Hello there. Today we're having a look at the global circulation. The Earth is not a simple sphere. The distribution of continents and oceans, the fact that energy in at the equator is much greater than energy in at the poles, the difference in angle of the sun, all sorts of things contribute to creating the complicated air circulation that we see in the satellite photo courtesy EUMETSAT. But even though it's complicated, there are some patterns we can clearly see. Along the equator there is this band of storms, and then in the mid-latitudes you see these great swirling storms in the northern and southern hemispheres, and then of course the great hot deserts of the Sahara and the Kalahari. Right, we know that the equatorial regions have much higher energy in than the polar regions. So what happens to this energy in? It causes air to warm and expand, it causes evaporation off the oceans, and the net result is that warm, moist air rises at the equator. We've greatly exaggerated the vertical movement here so that we can see what's happening, but nevertheless we've got rising air at the equator. When it reaches the top of the troposphere, it spreads out. Now, of course, this rising air at the surface needs to be replaced. So we have air flowing in from north and south of the equator, as you see there, from the north and from the south, to create a zone of convergence along the equator, the intertropical convergence zone. And then it rises and cools, and then it's going to sink. And it sinks at about an average of about 25 degrees north and south, 25 degrees north and south, and these zones of sinking air are called anticyclone. And then also we have sinking air in the polar regions. This is cold air sinking in both poles, and also that air spreads out. So we've now got two different kinds of high pressures. We've got a hot high pressure where dry air is sinking, and as it sinks it's compressed and heats up. And here in the polar regions we've got air sinking because it's heavy, because it's cold, and spreading out. So either way we're going to cause high pressure systems called anticyclones. Now an anticyclone occurs when the rotation of the air, the circulation of the air, is opposite to the rotation of the Earth. The northern hemisphere rotates anti-clockwise from west to east, so it's going anti-clockwise if we look down on the pole. The southern hemisphere is rotating clockwise if we look down on the pole. So anticyclonic in the northern hemisphere means a clockwise rotation, and we'll explain more about that later. And anticyclonic in the southern hemisphere means an anti-clockwise rotation. Easy way to remember it, of course, is that the southern hemisphere, the sensible south that we live in, does what you would expect it to do. Anti-clockwise, anticyclone in the sensible southern hemisphere. Clockwise for an anticyclone in the non-sensible northern hemisphere. So that's a way of remembering that. Right, so let's just have a look at that process again. Warm, moist air rising becomes dry air sinking. Why is it dry? Because it rained along the equator, and that explains these cloud formations here. That rising air is going to cause this zone of clouds, and we'll have more to say about that in a moment. And then at the pole you've got cold air sinking. Right, those are the two drivers of a much more complicated circulation of what's happening in the mid-latitudes. So, intertropical convergence zone, warm, moist air rising. Intertropical means it's between the tropics, that's 23.5 degrees north and south. Convergence means that the air is converging. Where converge is happening, you're going to have air rising, cooling, and causing rain. And when it reaches the top of the troposphere, it is dry, and dry air is heavy, and so it sinks, is compressed, and creates the hot deserts. Then the polar highs, where the cold air is sinking, they create cold deserts. the Antarctic is one of the driest places on the planet. These high pressure zones, anticyclonic zones, are called the subtropical anticyclones, and we can use the word high pressure or anticyclone completely interchangeably. We label them H's for high when we draw our weather maps, but we can call them anticyclones equally. High pressure, anticyclone, completely interchangeable. Okay, so what is happening in this zone between the cold air sinking and the dry air sinking? This zone over here and over here. What is going on there? Right, so there is our basic circulation, and coming out of the high pressures we're going to have that anticyclonic circulation around the northern hemisphere polar high, and that is going to result in easterly winds there. Likewise, we have that anticyclonic circulation, which is anti-clockwise in the southern hemisphere coming out of that polar high, and that creates easterly winds over there. So you notice you've got westerly winds blowing in that direction, easterly winds blowing in the opposite direction. The net result is that creates what's called vorticity. In other words, if you have two winds blowing in opposite direction, it's like putting a pencil between your hands and moving your hands in the opposite direction, the pencil will turn. And so you get this tendency for the air to go around in a circle. That is called vorticity. Now that results in the formation of mid-latitude cyclones. So let's just go through that process again. Warm, moist air rising, dry air sinking, cold air sinking at the poles, intertropical convergence zone, warm air, polar high driving it. And then between your subtropical anticyclones and the polar high, we get the development of these mid-latitude cyclones. Okay, let's just remove the complication of the underlying map. And we now need to look at the names of the winds. The winds that are converging in the intertropical convergence zone are called tropical easterlies. The winds that are diverging out of the polar high pressures are called polar easterlies. And then on the northern or the poleward side of the subtropical anticyclones in the northern hemisphere, because of that clockwise circulation of the anticyclone, you're going to get westerly winds there. And likewise, because of the anti-clockwise circulation of the subtropical anticyclone in the southern hemisphere, you're going to get westerly winds there. And the net result then between the polar easterlies and the westerlies, you're going to get this opposite wind circulation. And that process that leads to that, there are high pressures, that process is called wind shear. These arrows indicating that you've got wind shear, two winds blowing in opposite directions right next to each other, leading to these vortices which become mid-latitude cyclones. Wind shear. And mid-latitude cyclones are low pressures. Now we need to say something about cyclones. All cyclones are low pressures, but not all low pressures are cyclones, because at the equator here we have a low pressure, the intertropical convergence zone. Now because this is on the equator, the effect of the Earth's spin, which gets stronger towards the pole, is more or less zero. And it's the effect of the Earth's spin that creates these vorticities that create these rotating masses of air. So along the equator there is neither cyclonic nor anticyclonic circulation, it is just low pressure or a convergence zone. So all cyclones are lows, but not all lows are cyclones. Okay, so let's now remind ourselves what is happening in the vertical dimension. If we put all of that together, we've got what's called the tri-cellular model. And we give these circulations that we've talked about names. The warm air rising and sinking is called a Hadley cell, and the polar air, cold air sinking and being replaced by warm air is called the polar cell. And in between these two, we used to speculate that there was then another cell going in the opposite direction. Now this is what's called a model. In other words, it's a simplification of the reality. Remember the complex satellite picture we saw. So this is called a tricellular model because there are three cells, the Hadley, the feral, and the polar cell in each hemisphere. And these are like big donuts going right around at the given latitudes. And this was how the circulation of the atmosphere was viewed in the 1920s, before they realized that in fact the feral cell doesn't really exist, although it allows an easy explanation of what's going on here. Because while there are definitely vertical circulations, air rising and sinking in the Hadley cell and air rising and sinking in the polar cell, in the feral cell there is not air rising and sinking. And this is a better depiction. So there again we have our Hadley cell, and there again we have our polar cell. But we would rather depict the surface circulation due to these vortexes, the mid-latitude cyclones, not as a vertical circulation, but as a horizontal circulation. So just to remind ourselves, Hadley cell, polar cell, and then what we've got in between due to these mid-latitude cyclones is what we call eddy transfer. So this is a horizontal motion. These are vertical motions where air is rising and sinking. This is horizontal on one side of the eddy. The circulation is going northwards, and on the other side it's going southwards. In the southern hemisphere the other way around, going southwards there and northwards there, because the low pressure goes anti-clockwise in the non-sensible northern hemisphere around a cyclone, and it goes clockwise around the sensible southern hemisphere in the cyclone. So that's called eddy transfer. Now this model is called the Palman model, and this is a simplification of the Palman model. Your syllabus only requires you to know the tricellular model, but you may come across the Palman model in some books, so we tell you about it. But either way, it explains the general circulation of the atmosphere. That concludes the discussion of the general circulation. In grade 12 we have a look at the detail of how these systems affect our and global weather.